All right, so hello everyone, and thank you all for joining in to listen on my topic about how to use CODESYS to set up an EtherCAT network and how to optimize EtherCAT performance on TI processors. To start off, I want to give a brief introduction. I know that Chris already gave an introduction, so just to reiterate, my name is Daolin Q. I'm an embedded systems applications engineer at Texas Instruments, and most of my focus or experience focuses on embedded Linux real-time networking applications on TI AM6 processors. And I have experience working with applications using EtherCAT, time-sensitive networking, and network redundancy protocols like HSR and PRP. So this is the agenda for my presentation today. I'll start off with a brief introduction of Texas Instruments as a company, then dive into the main content, starting off with a brief overview of EtherCAT, how to set up EtherCAT master on TI processors using CODESYS, some of the performance benchmarks that I've obtained with that setup, and some of the techniques that I use to try and optimize EtherCAT performance. And then I'll end off with some key takeaways of my presentation, and I believe at the end of all speakers' presentations today, I'll also be available for Q&A. So for those of you who aren't familiar, Texas Instruments is a semiconductor company that has employees worldwide. Most of our revenue comes from designing, manufacturing, and selling analog and embedded processing chips. And we cater to a wide variety of key markets with a special focus on industrial and automotive markets. As I mentioned, Texas Instruments sells both analog and embedded processing chips. Of course, our analog chips are well known across the world globally. However, we have several different families of embedded processing chips as well. The AM6 family of processing chips is especially designed for industrial application use cases, and currently it uses a 16 nanometer process node technology to offer the best-in-class power consumption, as well as these devices ensuring capacity and longevity over the long term. And we also have a unified software architecture built specifically for AM6 family processors. So here is kind of a quick overview of the portfolio of our AM6 family of processors. We cater to a multitude of different sectors within the industrial application use case, including general purpose, networking, and real-time control, which are especially relevant for a PLC end product. So I know most of the audience is probably already very familiar with EtherCAT, so I'm going to keep this slide quick. Basically, EtherCAT uses a master or a main device setup where it controls a series of slaves or sub-devices that are typically configured in the daisy chain setup. The EtherCAT protocol is especially useful for applications like motor control and robotics, where strict deterministic and time synchronization requirements are necessary. And the protocol can claims down to 100 microseconds of cycle time in terms of speed performance, and down to 1 microseconds of deviation in terms of time synchronization capabilities. So in terms of speed requirements, the main performance metric for EtherCAT is EtherCAT cycle time, which is essentially a time it takes for an EtherCAT frame to travel from the main device through the various sub-device nodes and back, as well as time needed to process that EtherCAT packet on the main device. Typically, what we've seen is that EtherCAT cycle time typically has a cycle time requirement of 1 milliseconds. And here I tried to show a very simplified view of the various timings that contribute to an EtherCAT cycle. These timings include, from the main device side, time it takes from an EtherCAT frame's process data to be received, time it takes for any logic to be processed, on that received process data via the application task, and then time it takes for that process data to go back out onto the network. Additionally, there's time needed for the EtherCAT packet to actually travel through the various sub-device nodes. And not shown in this diagram is additional timing likely due to DMA channel processing, whether on the main device or sub-device sides. So in order to benchmark EtherCAT cycle time, I of course need an EtherCAT setup. So in my setup, I used a TI evaluation module featuring the AM625 microprocessor, which itself features 4 ARM A53 cores and up to 1.4 gigahertz of CPU frequency. This will serve as the EtherCAT main device, and from one of the Ethernet ports on the evaluation module, I have connected 11 Beckhoff I/O devices that are serving as the EtherCAT sub-devices. These devices include one EtherCAT coupler and 10 16-channel digital output modules. On the other Ethernet port, I have connected with a Windows PC that is going to be running CODESYS development system. In terms of software setup, as I mentioned, the Windows PC will be running CODESYS development system to be able to set up, configure, and monitor any statistics on the EtherCAT master. On the evaluation module, I have flashed the latest TI SDK Yocto built image that uses RT Linux, and on top of that, installed CODESYS control for Linux ARM64 using an IPK package. Additionally, I installed CODESYS control standard S license so that I can enable longer run times than 2 hours. From the sub-device side, I had configured a structured text program in the CODESYS development system to toggle all the channels on the digital output modules between high and low every 1 second, and I configured the cycle time to 1 milliseconds. For additional information on the specific steps I took to set this up, you can feel free to take a look at the application note on the top right here, top right link here. So first, I wanted to obtain a baseline metric of EtherCAT cycle time, essentially a metric that doesn't involve any changes or tunings on top of the software setup that I explained in the previous slide. With this setup, or with this test, after a 63-hour runtime, I observed that the maximum cycle time reached up to 739 microseconds, and the combination of maximum receive time and maximum send time of a packet comes up to 538 microseconds. So that makes sense because this would contribute to the cycle time itself. And then EtherCAT task, which is the task that's actually running the structured text that controls the sub-device modules, is by default running on core 1, the second core of the 4 A53 cores on AM625 processor. From the CPU load view on the CODESYS development system, I noticed that there are spikes occurring on core 0, core 2, and core 3 in terms of loading. However, interesting enough, the core that's running CODESYS EtherCAT task is actually not spiking much at all. Another thing I noticed is that with the monitor view that I showed previously, where a user can view different statistics like cycle time, that view doesn't allow us to see the statistics and how they change over time. And so within the CODESYS development system, there is a way to add a trace object so that any specific statistic that the user wants to view over time can be plotted in live in a plot like this. And so from this view, I can see that most of the time, the cycle time is actually less than 400 microseconds, with only occasional spikes up to 600 or 700 microseconds. And additionally, I noticed something interesting is that the cycle time seems to increase every approximately 10-second interval. Without this view, you cannot see the granularity of when these different changes that are happening to the cycle time occurs. And this view allows us to kind of see where, at which point in time, is something occurring with the setup that may have been influencing cycle time and causing these increases. From the evaluation module itself, I can run htop on the serial console to see a list of various background processes that are running on the processor and taking up CPU load. One thing I noticed right away is that the CODESYS license application called CodeMeterLen periodically takes up a significant amount of load and seems to load across cores 0, 2, or 3, but interesting enough, not on core 1, the same core that EtherCAT task is running on. Additionally, I noticed that a process called RQ balance is running, which is essentially a process that load balances the processing of hardware interrupts across all the different cores on the processor. Additionally, I noticed that there are many processes that are actually not needed specifically for EtherCAT communication that also take up some load as well. So from those observations, I already came up to some steps that could be taken to try and tune the performance a little bit to become a little bit more optimized. The first thing to try is to disable any of the unnecessary processes that are running, of which I included some, but not all, that are included in the default TI SDK image that are used to show an out-of-box demo for other applications, but not specifically useful for EtherCAT. Additionally, because RQ balance automatically puts load on various cores to process hardware interrupts, by killing RQ balance, we enable more control over setting which CPU affinity various hardware interrupts should be loaded on. Additionally, as I mentioned, CodeMeterLen seems to be loading across core 0, 2, and 3, but not core 1. So it might be an interesting test to see what happens if CodeMeterLen is assigned to a CPU affinity of core 1, the same core that EtherCAT task is actually running on. At the same time, we can change the scheduling policy of CodeMeterLen from the default non-real-time scheduling policy to a real-time friendly one like sched FIFO, for example. And this in turn allows us to have control over changing the priority of CodeMeterLen as well. Another thing I noticed was that when the evaluation module is booted up, this AM625 processor is actually loaded running with a 1.25 gigahertz CPU frequency, which is not the maximum CPU frequency of 1.4 gigahertz. So it might be also an interesting test to see what happens if the CPU frequency is increased as well. In Linux, there are processes called ksoft RQD that are essentially processes used to when the case of when there's a lot of pending soft RQs due to, for example, a high amount of incoming Ethernet packet interrupts. By default, ksoft RQD is initiated with a non-real-time scheduling policy, and so it might be a good idea to try and change the scheduling policy of ksoft RQD to a real-time friendly one, and at the same time, elevate its priority. Lastly, there is a concept called real-time scheduling time in RT Linux that is essentially a limit on how much time is allocated to actually process real-time scheduled tasks. By increasing this global limit, we can perhaps enable more time for these real-time dependent tasks to run and less likely for it to miss its deadline. Although I listed some various methods to try and tune the performance and see how it impacts EtherCAT cycle time, this is not an exhaustive list. And there are other additional techniques like core isolation that could be used as well. And so if you want more information about other things that can be tried out, please feel free to check the checklist in this link on the top right. So I mentioned there are non-real-time scheduling policies and real-time scheduling policies several times before. And essentially what I wanted to bring up was that most of the processes that I observed, like CodeMeterLen and KSoft R2D that I mentioned before, by default get initiated with the sched other policy. Well, in other words, the time sharing policy, which is typically used for regular non-real-time tasks. It might be a good idea to change these processes that have direct relation to CODESYS EtherCAT runtime to a real-time friendly policy like sched FIFO, which is essentially a first in, first out policy that allows any task with this policy to preempt any task with sched other policy or any task with sched FIFO a policy with a lower priority. For the purposes of this presentation, I just want to focus on sched other and sched FIFO, but if you're interested in some of the other policies that are listed here, feel free to go to the Linux Foundation page that details more about the other policies as well. So I also want to bring up a Linux utility tool called cyclic test that is commonly used to measure system latencies caused by hardware, firmware, and the OS. This tool essentially allows us to plot a histogram-like plot to show the spectrum of system latencies that you would observe on that specific hardware. For the AM625 processor, I show here on the right a histogram plot of the spectrum of system latencies observed on the processor when the CPU cores are loaded through the stress-ng application. This cyclic test result allows us to see what the hardware system latencies are that can contribute to, for example, an EtherCAT cycle time metric. And so it might be a good idea to also try running cyclic test with heavy Ethernet traffic load. Doesn't necessarily have to be EtherCAT specific, and perhaps adding core isolation to dedicate a specific core to be the real-time core could be a good first step before measuring or going through the trouble of setting up a full-on EtherCAT network to measure EtherCAT cycle time performance. Another topic I want to bring up is that there is an organization, for those of you who may not be aware, called OSADL that specifically publishes cyclic test results on many different embedded systems platforms, including Texas Instruments, as well as other silicon vendors. Essentially, this organization manages and hosts a quality assurance testing farm that tests cyclic tests as well as other various tests on different hardware platforms. So it might be a good site to kind of evaluate what all the different options are for your hardware. So after employing all of those various tuning steps, after an 18-hour runtime, I observed that the maximum cycle time comes up to about 645 microseconds. This is actually close to 100 microseconds of cycle time improvement or decrease from the baseline that we observed before, simply by applying those various tunings on top of the already running software setup. Additionally, from the CPU load view, I noticed that all the previously seen spikes occurring on core 0, 2, and 3 seem to be moved now to core 1. And the only process that actually set a different CPU friendly to was actually CodeMeterLen. and so can make the inference that most likely the spikes observed on the other cores previously were likely due to the code meter lin application. Additionally, from the trace object view, I see although that most of the cycle time is still less than 400 microseconds, the occasional spikes only occur up to about 600 microseconds now. And I also noticed that the cycle time increase that seemed to occur approximately every 10-second interval is now not present. Although those were some techniques that can be used to try and tune for a real-time system, there are other promising optimization techniques, such as Ethernet interrupt separation. Due to the nature of the network setup, there's essentially what I call two different Ethernet traffics going through the system. There's one that I call monitor traffic, which is essentially the traffic between the Windows PC with the CODESYS development system connected to the EtherCAT main device. And then the other traffic is essentially the actual EtherCAT traffic that travels between the sub-device nodes and the EtherCAT main device, which essentially does have strict real-time requirements. Although these two traffics are passing through two completely different ports, that doesn't necessarily mean that processing of the traffic from these ports are not going to be using shared resources. Because there might be a chance that shared resources are used to process both non-real-time and real-time traffic, there may be interference with real-time and causing some additional cycle time latencies as well, EtherCAT cycle time latencies as well. And so one way to try and separate out processing of these two traffics is to separate, for example, the receive Ethernet interrupts between the non-real-time and real-time traffic. And specifically because we're using the evaluation board for the AM625 processor, which itself uses TI's Common Platform Switch, or CPSW, MAC ports, there are specific steps needed to actually separate the RX interrupts from each other. And these steps include first to map traffic from the specific port based on the port's MAC address to a specific RX channel. And also, the second step is to disable RQ balance if not already done so that the operating system doesn't automatically change which CPU core is actually processing each of these different hardware interrupts. And this essentially allows us to do step 3, which is to assign a specific CPU affinity for the mapped RX channel so that we can separate out processing based on a specific core for between non-real-time and real-time RX interrupts. So I first wanted to validate that interrupt separation is actually working without, just as a base, without any EtherCAT setup. So for this, what I did was to map the first port, Ethernet port 0, to RX channel 0, and set the CPU affinity of RX channel 0 to core 3. And for the other ports, I mapped to RX channel 5 and set the CPU affinity to core 1. Afterwards, I performed a test by simply pinging 100 packets through port 0 and about exactly 500 packets through port 1. And I expected to see that port 0 and port 1 increased in about the same amount of interrupts. And what I see was actually about 164 interrupts increased on the channel mapped to port 0, and about 502 interrupts mapped to port 1. And I don't see any increases in interrupts across any of the other fields within proc interrupts as well, indicating that the only cores that are actually processing packets are on cores 3 and 1, and only on RX channel 0 and RX channel 5. So this kind of gives me confidence and proof that interrupt separation was successfully set up. And so from there, I applied it directly onto the EtherCAT setup, where now I have the port with EtherCAT traffic mapped to Rs channel 0, set to a CPU affinity of core 1, and the monitor traffic mapped to Rs channel 5, and setting the CPU affinity to core 3. I essentially want to set the EtherCAT traffic mapped to a CPU affinity of core 1 so that the traffic, the ARX interrupts from that traffic is handled on the same core that EtherCAT task is running on as well. So after a 67-hour runtime, I noticed that only the R channel mapped to EtherCAT traffic increased about 200 million interrupts, and the R channel mapped to monitor traffic increased about 8 million interrupts, and that there are no other increases on any of the other R channels and other CPU cores, indicating that this interrupt separation setup is also successfully working on the actual EtherCAT setup. And so after the 67-hour runtime, I noticed that the maximum cycle time came up to about 505 microseconds, which is about approximately 200 microseconds improvement from the baseline that we observed in the first test. So this kind of shows promising effects on not only using interrupt separation, but also processing those interrupts on the same CPU core that EtherCAT task is running on. Another optimization technique that I wanted to explore is the concept of using an XDP driver, which is quickly gaining traction in the Linux community as a way to decrease the amount of latencies caused by processing a packet from the user space level. Essentially, with the traditional networking stack, an Ethernet packet needs to travel through many different networking layers to reach the user space application before the packet can be processed. But with a XDP or with a network driver that has XDP support, the Ethernet packet can essentially be processed as close to the hardware as possible, thereby bypassing a lot of the networking stack layers within the kernel space itself. And so what this means is that since CODESYS control for Linux ARM64 is the user space application in our setup in this case, if we can use an XDP-friendly network driver to process the EtherCAT packets early on in the networking stack layers, and then directly pass those processed Ethernet packet to the CODESYS control user space application, we can bypass a lot of the system latencies caused by traveling through each of the networking stack layers. Specifically, there is a variation of XDP called XDP zero copy that seems to be the most effective for user space applications, since it doesn't require any copying of the packets from the driver to the user space application, which itself can add additional delay, as it simply can pass directly the packets from the driver to the user space application. And what this means is that not only does the driver need to have XDP zero copy support, but the user space application should also be able to implement logic to receive these packets that are passed from the network driver. For the Texas Instruments CPSW network driver, currently we have support for XDP, but not yet for XDP zero copy. We have plans we already are working on implementing XDP zero copy into our CPSW driver and upstreaming to the Linux mainline community as well. And we would like to work with CODESYS to be able to test out this theory that using an XDP driver, the EtherCAT cycle time can also be improved as well. And so I just want to end off my presentation with some key takeaways. First, baseline EtherCAT cycle time can be improved with various real-time tunings, as I've shown in my optimizations slide previously. And it seems to be the case that processing tasks and interrupts like for example, the code meter len and the RX interrupts for EtherCAT traffic to core 1, the core that's actually running the structured text logic, seems to offer the best cycle time improvement. And lastly, XDP, specifically XDP zero copy, in theory seems to be promising as a method to achieve even better cycle time performance, but this has yet to be tested. So this ends my presentation here. Again, my name is Daolin Q. I'm an embedded systems applications engineer for Texas Instruments. And you can learn more about the specific TI processors that I used in my test setup at these links here, as well as the link to the evaluation module featuring the same processor. And I also have here the link to the application note detailing a lot of the steps that I performed that I presented in this presentation.